Hello, and thanks for joining us today for the latest Analytical Cannabis webinar, the Analytical Landscape of Cannabis Testing, Session 3, Pesticides and Mycotoxins by 𝗖𝗵𝗲. I'm 𝗧𝗵𝗲, Editorial Director for Analytical Cannabis, and I'm here to moderate today's event. I'm really pleased to have Karl Oetjen joining us today as your presenter. Karl is a Senior Scientist at SCIEX in the Technical Marketing Group. Before joining SCIEX, he completed his PhD at Colorado School of Mines in hydrologic science and engineering. In Karl's current role, he has worked with numerous cannabis testing labs across the United States who are focused on both quantitative and qualitative screening workflows. Following the webinar, we will have a Q&A session and we'd welcome any questions that you may have. Please ask questions using the Q&A system to the side of the video player. If you experience any technical issues during the presentation, please contact us using the chat system. And with that, I would now like to hand over to Karl.
Thanks so much for the introduction. I'm happy to be here today, and I'm happy to talk to you guys about what's going on with 𝗖𝗵𝗲 in cannabis testing. So we're going to be talking about the role that 𝗖𝗵𝗲 fills with pesticides and mycotoxins in particular. When we think about cannabis analysis and all of the different parts that make up cannabis analysis, there are a few different areas that 𝗖𝗵𝗲 kind of fits into. The two most commonly thought of ones are definitely pesticides and mycotoxins. Some folks are using 𝗖𝗵𝗲 to look at terpenes in addition to cannabinoids, although it's a little less common. So we're going to really dive into the pesticide portion. And if you're unfamiliar with LC and its role, but you maybe have used GC before in the past, there are a lot of similarities, but there are also some differences. So for GC or gas chromatography, obviously the compound must be volatile compared to liquid chromatography where it must be soluble. So those are the two big distinctions between the types of analyses, or at least the requirements of them. Another thing that is really important is that sometimes some thermally unstable compounds might decompose in gas chromatography. And that's going to become really important because depending on the pesticide list you intend to evaluate, some of those compounds are very thermally unstable. So liquid chromatography kind of fills that gap where it can be operated at room temperature. Additionally, we're going to be looking at some larger compounds. So for the most part, traditional GC compounds are usually under 500 Daltons, where using LC, we would analyze up to 100,000 Daltons. So a wider mass range, but regardless, both are quantitative, both are reproducible, and both are robust. So what is an 𝗖𝗵𝗲 and how does it work? So I know last session we talked a little bit about GC-MS, but we'll talk about 𝗖𝗵𝗲 in the sense that the liquid sample is being introduced. So we have an autosampler that is spraying essentially a spray into our mass spec. And that spray, the molecules of interest are then being converted into ions. And then under an electrical field, they're being pulled through a mass spectrometer. And here they're being transmitted and selected for and eventually fragmented. After this part, they're being detected by some sort of computer and then being transmitted into curves and etc. But what is the real experiment that's happening and how are these things being selected? So for 𝗖𝗵𝗲, we're going to be talking about MRM scans specifically. So these are going to be our quantitative scans that we're using for our pesticide analysis. So in our first step, we have 4 ions that are entering our Q1. And we're really only interested in one of these ions. In this case, we're only really interested in the green ion. So we're going to use our Q1, our first quadrupole, to filter out the other ions that aren't of interest. So when we do that, we'll have our green or our 215 move into our Q2. So quadrupole 2, or commonly referred to as the collision cell, is where we're going to create some fragmentation. So you'll hear folks talk about the parent ion and the daughter ion, and Q2 is where we create those daughter ions. So we're going to apply some energy. There's some nitrogen gas there that promotes the fragmentation. And now we have a series of fragments. But for an MRM scan, we're really just looking at one ion or one daughter ion. And in this case, we're going to look at that 185. So for the Q3, we're going to filter out those remaining ions just like we did before. And we have our one single transition, which would be from our 215 to our 185. And you'll see why this is important later, but essentially what we're doing is we're being highly selective. So instead of worrying about if we have a compound with a similar parent mass of 215, or maybe it does have a mass of 215, here we're looking at a daughter ion. So it's very unlikely that it would have a mass of 215 and also a fragment of 185. So we're using that selectivity to be very specific. So what kind of data does this give us? Technically, it's giving us a mass. It's a ratio of mass to charge. And it's giving us an intensity of the detected masses. But how we're using this data is a little bit more complex than that. You can use it for quantification, which is what we're going to be talking about today. But you can also do things like discovery work, looking at molecular formulas, or looking even at fragmentation patterns. So why does it matter? Why do we care about MSMS? Why not just use a traditional single MS scan? Why do we need that fragmentation? So here we have an example of MGK. So this would be a pesticide we look for in a lot of the lists, at least in the Americas. Traditionally, the Oregon list would contain this compound. And in the green, we have a standard. So we see our two nice isomers for MGK 264. And if we move one panel over, we have a matrix blank. And in the matrix blank, we notice, oh, there are two things that look very similar to MGK 264, but they're coming out at a slightly different retention time. I'm not sure if those are actually the pesticide of interest. In this case, they definitely aren't, because this is a true blank matrix. But you can see how this would be kind of confusing for an analyst. It would be pretty easy to accidentally integrate underneath one of those interferences and think that, yes, I am looking at MGK 264. There's just a little bit difference retention time. And when we spike that sample, we see, oh, okay, even with the spiked sample, there isn't baseline separation. It would be really difficult to quantitate using this data. So this is where MRM data comes into play. So we have our MRM experiment where we have our standard. Again, we have those two nice isomer peaks. But then if we look at our matrix blank, there's nothing there. So we don't have those same interferences. And we've removed them by being more selective. So instead of just looking at that parent ion, now we're looking at the transition. And we can see in the spike sample, our recovery of our MGK 264. We have those two nice isomer peaks at the retention times we expect. So we don't have to worry about integrating shoulders or, worst case scenario, potentially misintegrating a peak. So for this example in this presentation, I'm going to be talking about specifically the Oregon list. This list is composed of 59 pesticides, with really 5 of them being traditionally thought of as GCMS compounds. We're going to do this all by LCMS. So for those GCMS compounds, we're going to be using a technique called APCI. And if you're unfamiliar with APCI, traditionally in GCMS, you would use an ionization type called EI. Here with LCMS, the most common ionization type is ESI, and APCI is kind of what bridges the gap between the two. So it can kind of dip into that GC world while also remaining in that LC world. So it can be a pretty valuable tool for some of these more challenging compounds. So the way we're going to discuss pesticides and cannabis analysis, we're going to look at it as kind of a holistic approach of how do we sort of validate our methods, how do we validate our LCMS systems. We know cannabis is an extremely challenging matrix to work with. So in order for our tools to be successful, they really need to be sensitive. Almost all the cannabis pesticide regulations require really trace level measurements. They also need to be flexible. So cannabis matrices come in a variety of form, right? We have foods, we have flour, we have waxes, we have shatters. The amount of matrices is really endless. And then equally important, it needs to be a robust method. It needs to be a robust system. Cannabis is probably the most challenging matrix I've worked with, aside from oil and gas wastewater. This is a really challenging matrix and poses some really unique challenges too. So from your LC-MS system all the way down to your pipettes, you kind of need to evaluate them using these 3 parameters if you want to be successful. Perfect. And for the LC-MS method, we'll be using the same method for all 3 studies. I'm just showing the ESI method. The APCI method is just a little bit shorter. But for both methods, we'll be using the 𝗵𝗲 𝗔𝗱𝗆𝗄 polar common. And this column is really good at retaining some of the more polar things like diminazide, which can be a little bit challenging. Great, so let's dive into the data. First, we'll talk about the matrix effects. So this is going to really get at the flexibility of your method. So when we were evaluating our method, we wanted to try a few different matrices. So we stuck to flour, cookies, chocolate, granola bars. We threw in some hard candy and also looked at some chips. And we extracted these using the CEM Edge, which we'll go into the details a little bit more, but essentially it's similar to a liquid-liquid extraction using acetonitrile. And our real goal here was to determine the suppression. So what's happening, what's this matrix doing to our system and our signal? So for our first part of the study, we essentially spiked our extracts after extraction. So this was done to really get at the matrix impact. So we wanted to exclude anything from recovery. We didn't want that to be a variable. We just wanted to see how the matrix affected our signal. The second portion was to look at the recovery of our method. So using this extraction approach, how good is our recovery for these pesticides in these varying matrices? So to do this, 300 milligrams of each matrix was extracted into 5 replicates, with the final volume being 30 milliliters of acetonitrile and 0.1% formic acid. In the matrix impact study, it was spiked after. In the recovery study, it was just spiked before, and this ends up being a 1:100 dilution. So I get asked pretty frequently, why do we use formic acid? So we use formic acid for stability reasons. So in the purple box, you can see 𝗧𝗵𝗲. So if you store 𝗧𝗵𝗲 under basic conditions without any formic acid, so just straight extract, what you'll notice is that you'll start to see this 𝗧𝗵𝗲 degradation product forming. And we really want to prevent this conversion as much as possible. And the same thing happens with Captain. So if you put Captain into your matrix and let it sit for a few days, or even just in a neat vial itself with no acidification, after a few days, it pretty much disappears. And Captain can be a pretty challenging compound as it is. So we really want to prevent this from happening as much as possible. And formic acid is a good approach for doing that. Another common question I get about sample prep is why I choose to do a winterization step. And the reason being, if we look on the left-hand side, these are my extracts. So they're example extracts. You can see they're pretty clear at a 1:100 dilution. There's a little bit of tint in the flour, which is in the middle, but for the most part, they look pretty clean. However, after I stuck them in the freezer at -20 degrees Celsius for about 2 hours, we've got all this fat precipitating out. So in the cookies and the chocolate, we see just a ton of precipitant. So we've done some studies at SCIEX to try to figure out if the winterization step is causing the losses of any compounds, or if it's improving the matrix or limiting the matrix impacts from these matrices. And essentially the answer is no. So we haven't seen any losses in compounds, and we also haven't seen any improvement in terms of matrix impacts. So, why bother doing this if it doesn't seem to be helping? And the real reason is it seems to help with column longevity and just keeping the system up longer. So even though it's not helping with our recoveries or the matrix impacts, it is increasing the amount of time we can keep our instrument up and running longer. Perfect. So let's dive into some of the data. So we have our hard candy or chips, chocolate, cookies, flour, and granola bar. And we're just going to look at some of the more interesting compounds. So in this slide, we have acephate. So acephate is one of our early eluters. So we want to get an idea of how's the front end of our chromatogram looking? Is there a bunch of suppression in the front end? And what we kind of see is no. If we draw a line just normalized at the top of the hard candy, everything is pretty similar. There's no big drops. You don't see cookies, for example, being half as high as acephate. So this is kind of telling us that, yes, what we're doing is pretty flexible. All the matrices seem to be roughly the same, at least for acephate, across the board. And next, if we look at 𝗧𝗵𝗲, which is the last eluting compound, we'll see something a little bit different. And 𝗧𝗵𝗲 is a really important compound. I like to call it the canary in the coal mine, because if you start to see 𝗧𝗵𝗲 disappear, it's a really good sign that your standard is starting to go bad. If water gets into your standard at all, 𝗧𝗵𝗲 will degrade pretty rapidly. So it can be a good clue to see if you're handling your standard right. So when you're taking it out of the freezer, for example, you're letting it come to room temperature before opening it. You're not letting any condensation get in there. It can be a pretty valuable sort of flag for when it's time to throw out that calibration curve and maybe make a new one. But if we take a look at our peak heights, we'll notice that flour is quite a bit lower than the other compounds. And that's something you're going to notice quite a bit. Flour tends to be a really challenging matrix. And I would say almost the most challenging matrix, even over the waxes and oils and isolates. Flour, because it varies so much, and in this case, this flour is the composition of 5 different strains. You see a lot of suppression and a lot of variability just between the strains themselves that you don't see with other matrices. Next, let's look at 𝗲𝗲𝗪𝗪𝒪𝒧𝒪😃. So 𝗲𝗲𝗪𝒪😃 is a very temperature sensitive compound. It's the reason we have to run this method at such a low source temperature, which is kind of too bad, because a lot of the other pesticides, in fact, I'd say almost most of the other pesticides, would prefer a higher source temperature. But when we get above 350 degrees Celsius into the really anything above 500 degrees Celsius, 𝗲𝗪𝗪𝒪😃 just really, the signal is really isn't there, and can be really hard to monitor for. But if we take a look at our peak heights here, we see the same kind of thing. Everything looks pretty in line with the exception of flour. So flour, again, is sort of being impacted more by this matrix effect phenomenon than the other matrices. So we're seeing more suppression essentially in our flour matrix. And pyrethrins. So pyrethrins are on the opposite side of 𝗲𝗪𝗪𝒪😃. They would prefer a much hotter source temperature, but again, not really an option because of 𝗲𝗪𝗪𝒪😃. And this is kind of interesting, where for the first time, we're starting to see a different matrix show some suppression. So we're seeing that in the chips. We're seeing a little bit of suppression that's kind of on par with the flour. which is a little interesting because chips and chocolate definitely had the most fat content of the matrices. So that doesn't seem to be the issue causing the suppression. So we'll dive in a little bit more into what might be causing that. And finally, we have our APCI compounds. Methylparathione, a traditional 𝗔𝗍𝗵𝗃 compound. Here we're doing it by APCI, and we get the same kind of result. One of the nice things about APCI is you don't have as many matrix effects as you do in ESI. So a lot of times, if you're going to do APCI, you might want to move over a few of your compounds, even if they do respond really well in ESI. If you move them over to APCI, you're less likely to be affected by some of these suppression issues that we're seeing. But overall, everything looks great, and you can see flowers right on par with our hard candy. And finally, we have chlorphenapyr. Chlorphenapyr, another traditionally GC compound, can be challenging in ESI, but in APCI, we get great recovery and very little suppression. So if we summarize all of our matrix effects, what we see is for all compounds, the matrix effects were between 70 and 130. So not a ton of variability there. Specifically, chips, cookies, and chocolates seem to have a tighter distribution, pretty near to 100, which is great. And obviously in this study, no internal standards were applied. If we applied internal standards, everything would be pretty much 100. So that wouldn't really be telling us how our matrix suppression is affecting our results. But flour really showed the most variability, and it showed the most suppression, which is kind of what I would expect, but can be a little bit surprising to some. And if we just take a look at each one of these compounds in particular, there are a few that you'll want to just keep an eye on in your own methods, specifically things like dimetazide that we didn't talk about would be another one that I would include when you're looking at matrix effects, since that is an extremely polar compound. But overall, everything was within that plus or minus 30%, telling us we're doing a good job and our method is pretty flexible. So let's look at our recoveries and see how we did there. So these would be spiked before extraction. And for acephate, again, early eluter, we see, okay, great. Everything is pretty in line with what we were seeing with the matrix effects. There's not something that just isn't being recovered well. So we don't see, for example, acephate have a really small peak in the chocolate compared to the other ones, which would be kind of a red flag saying this method isn't super flexible. It doesn't work well for chocolates. Same for acequinazole. We get a little bit lower response for our chips and our chips and flour, but that is just like what we saw before with their matrix impacts. So it's probably following along those same lines. Again, for ivermectin, we're seeing pretty similar results to our matrix effect study, where flour is just a little bit lower than everything else, but still not outside that plus or minus 30 range. And for our pyrethrins, great response here with flour and chips looking like they're pretty much on par with everything else in our study. Last but not least, we have our APCI compounds. So for methylparathione, this is great news. We're not seeing that some of these more challenging compounds are having lower recoveries. Everything is well within line of what we'd expect. And if we look at chlorphenapyr, we get the same sort of result. So that's great. If we summarize this data quickly, we can see our recoveries are lower. That makes sense. Chips, interestingly enough, had the most variability along with flours. So there's something there, some sort of reason that we're seeing this lower recovery, a little bit more of the matrix impacts than we were seeing with the other matrices. So kind of an interesting result. Ďiminozide recovery was about 40% by hand, so it's actually better using the CEM Edge. Ďiminozide can be a really challenging compound when you're doing any sort of sample prep, just because it is so polar. And you can see that here, if you take a look at Ďiminozide in the middle, you see a little bit more of that variability. But overall, just looking at the flexibility of our method at a 1 to 100 dilutions, we were able to see all the compounds in the organ list with the matrix effects, so no internal standard correction between 70 and 130, and our average recoveries between 60 and 101, which is great. That's right in the range that we'd want to be, and that's before any surrogate correction. So with a surrogate, we could increase those quite a bit. And Ďiminozide, because of that variability, I always suggest getting a surrogate for all matrices for Ďiminozide. And the Ďiminozide isotope label standard is pretty cheap comparatively, so it's a good thing to just throw in and add to your method. So next, let's talk about the sensitivity. So we know we're going to need sensitivity for a method if we're going to be analyzing these trace levels. So the way I like to get at sensitivity is essentially by making a matrix curve. I wouldn't use a matrix curve for quantification, but it is a nice way to get at what our expected limits of quantification are, or our lower limit in particular. So here we're doing the essentially same sample prep, except we're doing it by hand. Again, it would be a 1 to 100 dilution. And our criteria is we're really looking at the noise to our compound signal, and we're making sure that the compound signal is greater than 3x the noise, and the accuracy of that lower point must be within plus or minus 30%. So just to tie into what we were doing before, if we again look at acephate, that early eluter, in our isolate matrix curve, we can see, okay, great. Even at low levels, so 0.1 ppb in vial, so that would be 10 ppb in matrix. We've got a nice peak there that we can integrate. We've got a nice linear curve up to 1.5 ppm in product, or 15 ppb in vial. And with 𝗧𝗵𝗲, we're seeing the same thing. We don't see that degradation product, which is great news. And we have that linear curve that we'd expect. For ivermectin, we've got our LLOQ at 0.2 ppb, all the way up to, again, 15 ppb in vial. So we have a nice linear curve, a good R squared. That's letting us know that, yep, our method is meeting all our sensitivity requirements. And it will be important to just define what the sensitivity requirements are, since they vary so much. So in Oregon, we're meeting them easily since that's the list we're targeting. And in pyrethrins, we have the same result, with the exception, we do see this sort of peak coming off to the side. And pyrethrins are interesting because they are probably the compound you'll see the most interferences with. Some of these might actually be other pyrethrins, but there are a few that even in natural plant you'll see. We haven't quite figured out what they are, but you'll notice them. So you'll really have to rely on retention time in addition to your MRM transitions to make sure you're not integrating the incorrect peak. And finally, just our APCI compounds. So we've got good sensitivity for both our methylparathione and chlorphenapure. This is great news. It's telling us, hey, our method's going to be sensitive enough. It's flexible enough. Now we just have to decide if our method is robust enough to be able to handle these really challenging matrices. So the way we typically evaluate robustness here at SCIEX is by just injecting the sample a lot. So what we did was we took our extract, again, that 1 to 100 dilution, and we injected it 800 times. So to do this, we made a short 6-minute gradient. The reason we did that was just to save time. We're really more interested in getting as much matrix on column as we can than we are to have our full method, since just 800 injections would take too long if we were doing our traditional 20-minute method. But just to check how we're doing and assess our method throughout this run, we did go ahead and run a 20-minute method every 10th sample. So that way we can do some comparison analysis. So here we have thiacloprid, and we're showing no internal standard correction. So what we're looking at up top would be the XIC. So that would be thiacloprid across those 800 runs, every 200 injections. And what we see is it's staying pretty steady. If we go ahead and look at our bottom graph, we notice there's a slight decline, but it's still within our plus or minus 30%. So this is telling us, hey, even though it's starting to decrease, you're still within this sort of acceptable range. And we'll talk more about how to define that acceptable range. The big thing here, though, is that we're not using any internal standard. So if we were using an internal standard, we would expect this to just normalize out and be close to 100. And that wouldn't really be telling us anything about robustness, right? That would just be getting at whether or not our internal standard works, which is great. That's important too, but it doesn't answer our robustness question. An example of that can be seen here. So for this compound, we see this decreasing trend. It started at 100, that makes sense, since it's normalized to our area. And we see this decrease over time. So from injection number 1 to 800, it starts to deviate outside that plus or minus 30% line. We get this nice linear regression. If we correct that with an internal standard, though, we correct for that loss and essentially sensitivity. And we see almost a more straight line, which is what we'd expect. So this data, this IS corrected data, isn't really telling us anything about robustness. It is telling us that we picked a good internal standard, which is great. But we really want to take a look at that no internal standard correction data to decide, hey, where are we in terms of robustness and how long can my system be up? How many injections can I get through before I need to vent, clean, and do all that? And of course, it's going to vary between compound to compound. So you want to do this on a compound basis. So if we take a look at our compound, so this is the same figure as before, except now we're plotting just the intensity. And we fit a linear regression to sort of that decline that we were seeing before. So we see this nice linear regression, the nice Pearsons are just slowly declining over time. And what we can do with this data is go ahead and decide, all right, we know it's going to fall out of that plus or minus 30%. But that plus or minus 30%, what does that mean? That just means that we're seeing that deviation. It doesn't mean that we still can't meet our method requirements. To do that, we'll have to kind of figure out when it wouldn't meet our method requirements. So for the organ limit for this compound is 4 ppb in vial. So what we did was we essentially used this linear regression to predict at what injection would our peak be less than 3x our baseline. So getting back to that sensitivity portion we talked about earlier. And for this particular compound, at about 2,800 injections would be that time when that peak would no longer meet your sensitivity requirements. So this would be when you would have to go ahead and clean to gain that sensitivity back. And this is kind of important because if you're able to plan for your downtime, planned downtime is always better than unplanned downtime. So if you can predict ahead of time and get an idea of, how long it will be before you need to vent, before you need to clean, you can plan accordingly. And that just makes the whole process a lot less stressful for you, but it also ends up being less unplanned downtime, which means that, if it's unplanned downtime, you might not have an engineer ready to go on site to clean, or if you're cleaning yourself, you might not have all the supplies you need. Whereas here you can say, yep, next Thursday is when we're going to vent the instrument. So we talked about flexibility. Flexibility is really important for these methods because cannabis comes in so many different varieties. Calling it cannabis almost makes it seem too easy. We're really talking about plant analysis. We're talking about food analysis. We're talking about oil analysis, wax analysis. There are a lot of different matrices that make it very, very complex, and it gets complex very quickly. So ensuring that your methods are flexible enough to handle these matrices and that you don't need different methods for different matrices is really important. Sensitivity, of course, not just sensitivity in solvent, but also in matrix. Essentially, we want to make sure that we can see it in our matrix. If we can see it in our solvent, that's awesome. But if we can't see it in our product, it doesn't really matter. So an easy way to do this is with matrix curves. Again, I wouldn't recommend using a matrix curves for quantification, but using matrix curves to get an idea of what your sensitivity is in that specific matrix can be a really useful tool. And then finally, robustness. Because this matrix is just so nasty and so complicated, it contains so many different compounds and features, it's crucial to understand how this is going to impact your system, not just from an 𝗟𝗵𝗲 standpoint, from your pipettes, for your GC. Everything in your lab essentially needs to be robust to be able to handle this type of matrix.